In this video, I will show you a practical demonstration of the Mendeleev Meyer force project works. Specifically, I will walk you through the process of populating the library. I will be using a calcite sample for this demonstration. This calcite sample, displayed here, has two phases, hydrated and unhydrated phase. But for demonstration purposes, I will just simply refer to these phases as phase 1 and phase 2. So the first step is acquiring nanoscale force data from the AFM and plotting the force curve from the data. The process of acquiring force data with the AFM has been detailed in previous videos. So, I will go ahead and show you how to generate the force curve from the data. I have here the raw data for both phases of calcite, about 200 each. You can take as many data points you want. However, these raw data are in Igor format. They need to be unpacked into text format for onward processing in the Mendeleev script used in this project. So to unpack the files from Igor to text format, open the Mendeleev project file. This file is included in link below. Select the folder Unpack Igor 2015 April folder, and open it. Put all the raw data into the folder labeled Files. You will have to input the amplitude and volts value when you perform the experiment. You can watch the previous video on how to calibrate the amplitude and volts. In my case, it was 53 nanometers per volts. Then click OK. Now the script has changed the raw data from the Igor format into a Mendeleev-friendly text format. Now that we have the text file, let's go ahead and construct the force distance curve, FDC. To do that, copy the new text file, navigate back into the Mendeleev project folder, open the subfolder force, then the dataset folder inside. You can create a folder here and paste the text file in the new folder. Still, in the force subfolder, click on the force parallel March 24, 2015 Mendeleev script. Then click on the Run button. You will see a pop-up panel where you will have to input the parameters used during the AFM data acquisition. We also discussed the process of getting this parameter in the previous episodes. So you will have to input the spring constant, Q factor and amplitude and volts you used in the data acquisition process. Then you click OK. You will be requested to select the folder containing the text files folder, so just select it. Now the force curves have been generated. But we need to normalize all the force curves so that the minimal force will correspond to 0 on the tip sample distance axis. To do this, copy the process set file from the force subfolder. Then navigate back to the Mendeleev force project folder, look for the stats folder and paste it in the stats April 24, 2015. While still in this folder, click on the main statistics May 12, 2015 Mendeleev file and run it. You will be prompted to select a file. This is the process set, then click Open. You don't have to do anything here, just click OK. The force has been normalized now. This process also generated these files here. The all data stat file contains the DFAD and the force of adhesion. The DFAD measure the distances in the well of the force distance curve, as proposed in this journal paper. The value of these distances can be now employed as a table of input features for a machine learning algorithm to generate a model. We do that by making sets. So copy all the all-stat files and paste it into the Making Sets February 28, 2015 subfolder under the Mendeleev project folder. I will use these 4 data sets for training the model. That is the training and cross-validation files for both phases of calcite. Then run this file here and select the training set for phase 1 first. In the pop-up menu, input the name of the sample in the first field. Choose 1 to indicate it is a training set. Because I took 200 force data, I would like to make 4 columns of input so that I will average every 45 force curves. I choose 45 instead of 50 because I am assuming that 5 out of 50 force curves will be bad. Then click OK. Now these data has been input into the library. Repeat the same process for phase 2. The training file has been generated. All that is left is to generate the cross-validation set. So run the code again. Select cross-validation dataset for CalSat Phase 1. Give it a name. Select 2 instead of 1 to indicate this is for cross-validation, then 45 and then OK. It asks for another information. This is the training set we generated earlier. Select it and open. Repeat the similar process for the phase 2. This concludes the making of the feature library. These data can now be used to generate a model to predict CalSat Phase 1 and Phase 2 from any raw data. To generate the model, use the 2 files generated in the previous step and paste them in the subfolder Spectroscopy 2015 February under the Mendeleev project folder. Make sure to delete the previous file with such name before you paste them. For convenience, I rename this training set to Input Training Set. Then run the main script for the artificial neural network here. You can just click OK for the first pop-up panel. The second panel asks for the minimum and maximum lambda and the incremental factor of lambda. I put 3 here. The lambda here is the regularization term. A too low value of lambda would mean overfitting and too high value would be underfitting. So we have to within. So what we do is to check for the full range first and decide which is the best. So I just OK this value. The next pop-up I fills accordingly. Now this concludes the process of generating the model. Copy them, then in the Mendeleev project folder open the Check Performance Models subfolder and paste the copied model in there. Then back in the Check Performance Models folder, run the plotting code script, and you see several figures. We are interested in the F1 score here. F score of 1 is perfect. The first model of 2 layers and 2 units is good enough, so you can copy the model. Then paste into the subfolder identify under the Mendeleev folder.